All right, week 2, here we go. Again, the idea behind these videos, feel free to take breaks, make sure you're taking notes, and come with all the questions you have. We'll have a moderate sized video here to wrap up some stuff on energy, and then another video which will simply be a copy of what I've used in the past on sun angles. Please bring questions to class with sun angles. I'll probably open class Wednesday of next week, asking for any question that you might have on sun angles, and then of course bring them to lab as well. So when we ended class on Wednesday, we were at this point, the idea of we have this amount of solar energy reaching the top of Earth's atmosphere, that 1,368 watts per square meter, and what is happening to it as it goes through the atmosphere. And that's what we're going to work on here with this series of lectures, the idea of some of it making it through that transmittance, being absorbed by Earth and then being re-radiated. So we'll talk about some of the stuff, including the greenhouse effect, in today's video. All right, the first group here is going to be absorption. The idea of a percentage that about 20% gets absorbed by the atmosphere as it works its way down from the top of the atmosphere towards the surface of the Earth. And the idea is that we mentioned the term black body in class on Wednesday, things that absorb perfectly and therefore emit perfectly. And it was mentioned that the atmosphere is not a black body. It is going to be very selective in what it absorbs, and it's going to vary greatly depending on what the wavelength of radiation is. It's going to do certain things, for instance, to ultraviolet, and different things to things with the infrared spectrum. And so in the stratosphere, we have a lot of oxygen and ozone that absorb that ultraviolet radiation. This is a very good thing. It's dangerous to us as humans. And so what happens is that we got the O3, these absorb the ultraviolet radiation, breaks things up a little bit, and over time it will break down some of the ozone, but it does get replenished as well over time. We'll mention in some detail later in the semester about things such as the ozone hole and how that actually can be a dangerous thing, but that it has improved in the past couple of decades. What's very important, though, is that the majority of the atmosphere, and when I mention here the clear atmosphere, we're talking about free of clouds and other debris, so to speak, is that it's transparent to the visible portion of the electromagnetic spectrum. The red, orange, yellow, green, blue, indigo, violet, the Roy G. Biv, colors of the rainbow from about 0.4 to 0.7 microns in wavelength. Water vapor is going to do some stuff to some of the wavelengths that are a little bit longer, beyond 0.8, working into that near-infrared portion of the spectrum. And this is going to become especially important when we start talking about the emissions from the Earth, which are, as we saw with Wien's displacement law, going to be concentrated within the infrared portion of the electromagnetic spectrum. And so what you see here, and we'll have a few graphs that look like this, is what is being absorbed by certain constituents in the atmosphere. And then at the bottom, you see one that says total atmosphere. So basically what you're doing is you're taking all these different boxes, nitrous oxide, methane, oxygen and ozone, water vapor and carbon dioxide, and just overlapping these top 5 boxes to make the bottom image. What you're seeing then on the y-axis are from anywhere 0 to 100% being absorbed. And then you're seeing the different wavelengths from some of the ultraviolet or the very low wavelength the very short wavelength, all the way towards the long infrared portion of the electromagnetic spectrum, the very long wavelength and lower energy. And so again, we can see that certain things are going to really absorb well some of that ultraviolet energy. You see the ozone and the oxygen blocking nearly 100% of those wavelengths below about 0.3 microns. Very, very important stuff, but it doesn't do a whole heck of a lot to portions of the visible spectrum. You can see that water vapor here in the 4th section down doesn't do anything to the ultraviolet portion of the spectrum, but there are certain channels, certain portions of the infrared, both near and far, that are absorbed very efficiently by water vapor in the atmosphere. And then you will notice that there are other portions of the electromagnetic spectrum, namely within that visible portion, and then certain areas around, maybe about 7 and 11 to 12 microns that pretty much everything can pass through very easily. The atmosphere, as we put here, is generally transparent to these wavelengths. And this becomes, again, very important both in terms of what's able to make it through to Earth what is trapped as it tries to leave Earth, and then on another level, what are we able to utilize and see with things such as satellite? And so one term that has crept up in class a couple of times is the idea of albedo. This idea of why on days where you may not have a whole lot of sun, or the sun is actually kind of dim, but you have a fresh snowpack and you go outside and you're squinting and you really need your sunglasses, and that's because there's a large percentage of the incoming solar radiation that gets reflected by the fresh snow. In fact, if you look in this table right here, you can see fresh snow, 75 to 95%, depending on the sun angle, gets reflected. And so the definition here of albedo, percentage of that radiation that gets reflected by a surface, and it can be, well, ranging from almost nothing, values 3, 5 if you look at some of these, all the way up to such as 100% or 95 by that fresh snow. Really, if you talk about albedo, we're saying how reflective is the surface? Is it behaving like a mirror and effectively just sending everything right back? This is some of the reason, for instance, why when there is a fresh snowpack, it often gets very cold. The concept is, well, if you can't get that incoming visible radiation to penetrate the Earth and then get re-emitted in the infrared portion of the spectrum, we're not effectively heating the atmosphere. It's simply getting reflected back out towards the upper atmosphere and out towards outer space. We talk about it again as a percentage or a fraction. So the chart here is showing again the percentage reflected. And I do encourage you, even though I'll talk about it here for an extra moment, to take a little bit of time and look through some of these values here. How things such as forests, coniferous forests, pine trees are going to really not reflect a lot. The dark colors are very good absorbers. Whereas you have other things such as fresh snow getting up to 95%, but when it's been around for a while and it doesn't have that same sheen or gloss to it, the albedo decreases notably. You can see things such as a water body with a high solar altitude. In other words, when the sun is directly overhead, the water almost looks dark. It basically absorbs everything. But if you are ever on a boat out, whether it's a lake or even the ocean, and it's getting towards the end of the day and the sun's low on the horizon, and all of a sudden it's almost blinding, because if it hits it at a low altitude, kind of coming in at a really low angle, it just reflects right back off that water. And then you see other things, different clouds, cumulonimbus, the big puffy white clouds, thunderstorm clouds, large percentage as you get some of the ones closer to the surface that are grayer and not going to be as reflective. They have a much lower albedo. Asphalt road, I've brought that up many times in lecture already. Darker colors are going to generally absorb well. Think of almost the term black body here again. Albedo is a very important concept. I want you to be comfortable with this and understand it moving forward, because we will bring it up regularly. So take a little time, and if you need to ask questions or look things up in your book to get a little better familiarity with the term albedo. And so this is the summary of albedo. High albedo, high reflection, light colored surfaces, your snow, things like that. Low albedo, meaning high absorption or a low reflection. The dark asphalt surfaces, the coniferous forests, the street, the fact that if you walk from the grass onto the pavement, it just simply gets hotter. It absorbs much more readily, meaning it has a low albedo. And so if we have areas that have substantial cloud cover, that can really mean cooler temperatures. The idea that they are going to reflect a lot of the sun away. The idea if you fly up in an aircraft and get above the clouds, it's sunny up there, but you're simply not getting it down to the surface if there's a large number of thick clouds. And so, for instance, a lot of the upcoming days with some periods of snow are going to have cooler temperatures, in part because the sun's energy is simply being reflected away due to the higher albedo of the clouds. So aside from being reflected, we can also talk about scattering. Scattering is the idea that when particles are coming towards Earth, they may get sent off in a different direction. They may not make it all the way down to Earth's surface. They can get bumped into by some volcanic ash or some soot from a forest fire, or just other molecules in the atmosphere, like, as we put here, oxygen and nitrogen if you're reading the slides. This is going to send them in, well, sometimes preferred directions. And so it can be very dependent on the wavelength of what is hitting these particles. We'll talk late in the semester when we get into optics about why is the sky blue. Teaser, it's called Rayleigh scattering. It's going to scatter things in a preferred fashion. And so we get a blue sky. Think about maybe sometimes when it's getting to be late in the day and you get a red sky, and then sometimes clouds will even take on different hues. And well, the idea that if we're scattering a whole bunch of stuff, we can sometimes end up with very white clouds. And so oxygen and nitrogen, thinking back to the constituents of the atmosphere, make up almost 99%. They do a really good job of scattering blue-violet light. And that's in many ways why we get this preferred scattering, giving us a blue sky on a very nice day. And so the other percentage simply makes it through. It gets transmitted through. About half of what's coming down to Earth's surface makes it to Earth. We've already brought this up, but I'll mention it probably 2 or 3 more times before this video is over. The idea that you're getting the sun to reach Earth's surface and the Earth absorbs it because it's going to behave like a black body. It absorbs everything that's incident. But it's also then going to emit that energy, and this becomes critical. We'll talk a lot about that coming up here. And so what you have for the inset graphic is this proverbial 100 knots, or 100 units, I should say, of incoming solar radiation. We see the reflectance about 20%, some scattering and other reflecting due to an albedo from Earth's surface. About 30% is reflected or scattered. Another about 20% of it gets absorbed by the atmosphere and the clouds. And that, again, approximate 50% makes it down to Earth's surface. At that point, it is absorbed by the Earth. And it's re-emitted. That's what there is here. We're going to take that visible, primarily visible energy, think back to Wien's displacement law. We're going to absorb it by the Earth, but because the Earth is so much cooler, it's going to emit primarily at a different wavelength. It's going to emit in the infrared portion of the electromagnetic spectrum. Oftentimes we'll refer to it in the long wave portion. Much longer wavelength, much lower energy. But this is critical. This is why the atmosphere of the Earth that we live in is warm to the point of sustaining human life. I understand very well when you're viewing this video, it's pretty hard to think of the Earth as doing a good job of warming us up, since hopefully you watch this at some point when you're huddled in your dorm or your apartment with temperatures and wind chills outside below zero. But this is going to be why we are heated up. But we may be already thinking, I hope that you're thinking in some ways, if you're getting critical and assessing this from the collegiate perspective of, well, what about the clouds? And what about things going on in the atmosphere? Is all of this energy, this infrared energy being radiated by the Earth, going to simply go out to outer space? The answer is no. And so we revisit a similar but just different looking version of the earlier chart showing a bunch of things from methane to nitrous oxide to ozone to carbon dioxide to water vapor, and realizing that now that we're emitting in this infrared portion of the spectrum, in fact, you remember it's somewhere around 10 microns is where we're going to really focus on, that there are going to be times where there's water vapor that really absorbs a lot of this infrared energy. Or that carbon dioxide. Now we're starting to think a little bit about the greenhouse effect and this global potential for global warming. It's not going to do a whole lot to the visible portion coming in from the sun. It's going to do different things to what is leaving the Earth. And this becomes very important. And so we do finally talk about greenhouse gases and the greenhouse effect. Early in the semester, even though it is still early in the semester, even earlier in the semester, I discussed how the greenhouse effect is in many ways good. We need the greenhouse effect because otherwise we'd be pretty darn chilly. And that's something we don't need this weekend, is to be any colder than it already is. However, if we start to increase the concentration of these gases, we start to absorb more and more of the infrared energy being emitted by the Earth, and that can start to lead to more and more warming, and you start to have what's known as a feedback mechanism, which can cause increased warming over time. And so a number of these gases that we just showed on the previous chart, carbon dioxide, water vapor, methane, ozone, nitrous oxide are going to absorb different portions of the long wave radiation. And so what's happening is that the majority of what's sent away by Earth is actually absorbed by the atmosphere. And, well, we are still going to think of Kirchhoff's law. What is absorbed is being re-emitted or re-radiated. And so the thing is that not all of what is being absorbed by the atmosphere is being re-radiated down towards Earth. Some of it gets absorbed in the atmosphere and then just simply gets re-radiated the same direction it was trying to go in the first place, out towards outer space. So what you see here is the idea of what the Earth would be like temperature-wise if we did not have this greenhouse effect. The Earth would be a lot colder. We'd be talking 255 Kelvin. And so if you recall, 273 Kelvin is when we're at freezing. And so, we're talking some pretty chilly temperatures here. We're talking well below zero. That would be if we had none of these gases reabsorbing any of the outgoing long-wave radiation. However, the Earth does absorb. We can see that the atmosphere absorbs. Some of it then gets re-emitted back down to Earth, and that helps to warm us up a little bit more, to the point that the average Earth temperature is about 15 degrees Celsius, or if you're still not all that comfortable with your conversions, the upper 50s in terms of Fahrenheit. If we continue to increase these greenhouse gases, however, the atmosphere will simply absorb a greater and greater percentage, which even if the overall percentage of what gets re-emitted back out towards space stays the same, we're still going to be having more and more of this IR being emitted back down towards Earth, which is going to cause additional warming of the atmosphere. We do know that many of these greenhouse gases are increasing. We know from measurements that carbon dioxide in particular is increasing. Methane is increasing. And so these are going to be concerns as we move forward on how we can mitigate the potential impacts from these increasing greenhouse gases. And so why do we call it a greenhouse gas? It's the idea that it's basically like a greenhouse. If you've ever had the chance to walk into a greenhouse in summer, it's warm, it's muggy, it's letting the light in, but it's making it more difficult to escape. Greenhouses are used to basically grow plants when the outside temperatures may not support such behavior by keeping things a little bit warmer. Remembering, though, that the atmosphere is not a black body. It is going to selectively absorb at certain wavelengths, and this is where we're going to have to place our focus when we look at the greenhouse effect. Understand that some of the infrared energy simply gets right through. There's these areas that you may have noted in the previous graphics referred to as atmospheric windows. Basically, think of it as a hole in the greenhouse where it can simply escape out without any interference from the atmosphere, from the methane, from the carbon dioxide, so on and so forth. And so this is a critical piece of what we've talked about throughout these slides, and only a couple more to go if you're kind of on the ropes. The idea that the Earth is warmed from below. We are not being warmed directly by the sun, and yes, I know if you want to lay out in the sun, you will warm up because you will absorb the sun's energy. However, the atmosphere that we live in is simply being warmed by the infrared energy being emitted from the Earth. A little bit of conduction near the surface, but those convective processes have become very key. Again, thinking of the methods of heat transfer that we talked about in class. We'll talk a lot about how some of this convective activity can create things such as thunderstorms. It creates some of the upward and downward motions that become critical for having mid-latitude cyclones and other very interesting weather phenomena that we'll discuss throughout the portion of this class. And so this is a pretty complicated slide. Maybe we'll kind of start things off a little bit in class next week with these couple of slides. The idea that the numbers are a little odd, the concepts are what are critical. You do not need for an exam to start memorizing any of these numbers. What you do need to know is what can happen to this radiation as it moves through the atmosphere, both from the sun and after it's emitted by the Earth. Understand that as it comes in, it can simply be captured by Earth, it may be transmitted through, but that it may be actually scattered away, that it could be reflected away, so on and so forth. Understand that as it leaves the Earth, we can have the atmosphere send some back down, or we can have it send it back out towards outer space. And so there's a lot again going on here. As long as you understand the overall topics, you will be just fine. And so we conclude with this final topic. This will kind of segue us into the idea of sun angles. The idea that the sun is sometimes high in the sky here in Valpo, summer, and sometimes very low to the horizon, winter. In winter, the sun is at a very low angle, and we also have fewer days where the sun is up in the sky. We're at a period right now as we move into February where the sun's still pretty low, but we're at least getting a little bit more daylight each day. Regardless, you're going to have areas near the tropics where the sun is typically at a high angle with more hours in the day throughout much of the year, to where you get a surplus of incoming energy. Near the poles, where you have sometimes areas north of the Arctic Circle that have 0 hours of daylight for part of the year, you have a deficit in the energy. What does this mean? It means that the Earth is always trying to get into some form of balance. We're going to be transferring some of this heat near the equatorial regions out towards the polar regions. There's many ways we can do this. It can happen through the atmosphere, and it can also happen through the oceans. And this motion of air is ultimately going to start to be why we talk about weather systems, mid-latitude cyclones, hurricanes, so on and so forth. Ways of redistributing energy as the Earth always attempts to get into balance, but unfortunately never can succeed. And so this will become kind of a recurring theme as well as we move further on in the semester. So this video has been a little on the longer side. Hopefully you've made it through, taken breaks as needed, and we will see you in class on Monday. Have a good one, and stay warm.